Hello, 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 everyone. Hope you're all feeling fantastic and you're ready to finish off our 2017 Canadian Intermediate paper with B3. We call a positive integer balanced if it has 6 digits. Each of the 6 digits is non-zero, and the product of the first 3 digits is equal to the product of the last 3 digits. For example, 241, 181, so 241,181 is balanced since none of the digits are 0, and 2 times 4 times 1 is 1 times 8 times 1, which is just 8. Okay. So, brand new concept. Usually the way these sorts of questions go towards the end of the papers is they'll introduce a new sort of concept, and usually part A is just getting you acquainted. Did you understand what we just said? Sort of thing. B is usually a bit more of an investigation, and C or D, if it's a longer one, asks you to sort of come up with something that's a little non-trivial. Might be a little bit harder. So, A, determine with justification, because, well, we're still in the written portion of our paper, all balanced positive integers of the form 3b8d5f. Okay. 3b8d5f is balanced if what? Well, if none of these are 0, so we'll just be sure not to make b, d, or f 0. If 3 times b times 8 is the same as d times 5 times f. Of course, this is 24b, and this is 5df. Usually you put your numbers before your variables. Okay? So, well, what can we do? We need to figure out all the possible b's. Now, one thing, or not b's, d's, and f's. Okay? Now, one thing you can notice is 5 over here. 5 is a prime number. And prime numbers have a very nice property. If p is a prime and you know p divides a product, then p has to divide at least one of the factors of that product. So what I can see here is 5 must divide 24 times b. Right? So 5 must divide either 24 or 5 divides b, or maybe both. But of course, that one's impossible. So 5 divides b. So b is a digit. B can't be 0, but somehow 5 divides b. We conclude pretty quickly 5 must be b. And so we've got 3, 5, 8. D5f is our number. But I can work out what this is. 24 times 5, that's 120. And if I divide by 5 on both sides, I see that d and f must multiply to 24. And that's it. As long as d and f do that and we don't use any zeros, and of course you can't. If d or f were 0, the product wouldn't be 24, it'd be 0. But as long as we do that, we're good to go. So we just need digits that multiply to 24. That's the conclusion we've drawn from here. Okay, let's just quickly make a little chart here. Think of single-digit factors of 24. 5 isn't one, but 6 is, 8 is, 9 isn't. And so f would have to be, well, if d was 1, f would have to be 24. That's not going to work. 12, that's not going to work. If d were 3, f could be 8. 6, 4, and 3. Yeah, all of those are single digits for both the d and the f. So the balanced numbers are, do we want just the b, d, and f, or do they want all balanced numbers of the form? Okay, so 3, 5, 8 is not disputable. 3, 5, 8 if d is 3 and f is 8. 3, 5, 8, 4, 5, 6. 3, 5, 8, 6, 5, 4. Just reading off this chart that we made. And 3, 5, I better put commas in here just to show the different numbers. And then 8, 5, 3. All right, there we go. So we've got our balanced numbers. Very quick display of, do we understand the concept? And we do. So there's 4, and that's it. All right, let's get into B part. This should require a little more effort, a little more thought about, how balanced digits work, or these conditions up here. Determine, with justification, a 3-digit, do we just need a 3-digit? A 3-digit positive integer of the form 4bc for which there are exactly 3 balanced positive integers of the form 4b, c, d, e, f. So these last 3 numbers, I'm not being given part of them like I was in the last question with the 5. D, E, F, it could really just be anything. Interesting. So I need to figure out the first little bit that makes the last little bit not uniquely determined, but there can only be 3 of them. Okay, now we saw 4 in the last one, but we weren't exactly free to have the last digits be whatever we needed. Okay, exactly 3. Well, what can we say? For any balanced digit, or yeah, any balanced number. So they're giving me A is 4, really. If ABC is given, then A times B times, I better put the multiply sign in here. A times B times C must be equal to D times E times F. But if we take a look at the example that they gave us, that 2, 4, 1, I think, and then 1, 8, 1, if you knew the 2, 4, 1, if they gave you the first 3, which is what they're asking for here, they're asking me for 4BC. They're asking me for the first 3, and I want exactly 3 possibilities for the last 3. You could rearrange. We could have had 1, 1, 8, or 8, 1, 1 with that first one. Or there were other possibilities. You could have had 2, 4, 1 again, or 1, 2, 4, or 2, 1, 4, or 1, 4, 2, or 4, 2, 1, or 4, 1, 2. So it's you can get just from some numbers, so 1, 8, 1, a certain number of rearrangements, and that gives you possible numbers here. So what can we say? If D, E, and F are all different, there are 6 ways to rearrange them. Okay? You have DEF, DFE, EDF, EFD, FDE, and FED. And all of these can be preceded with ABC. But if the D, E, and F are all different, these are going to be 6 different numbers. And we don't want that. So when we pick our B and our C, we're going to want to make sure that there's no way to write A times B times C. That is to say 4 times B times C, because they told us the first one's 4, using 3 different digits. Okay? Now, if 2 of D, E, F are the same digit, there are 3 ways, and this I think is what we're going to want to focus on. So, let's say D and F are the same. You could have A, B, C, D, D, E, or D, E, D. There's just 3 ways to place that E, the odd person, out at the end. And finally, if all 3 digits are the same, we get 1 number. A, B, C, D, D, D. But that's only going to happen if A, B, C is a cube. Okay? But if you were only going to get sort of 1 number here, you have to get, you wouldn't be able to have different A, B's, and C's there as well. Okay, now I want to focus on, so we can't have 6 ways because they want exactly 3. Okay, so they gave me 4, I need to pick a B and a C so that I get exactly 3. 6 would be too many. Okay? So we might say, oh, okay, maybe we can have 2 of them the same and 1 of them different at the end. Or maybe there are ways to get 3 sort of cubes, and we can sort of dispel that idea right away. So if A times B times C, let's say if A, B, C, D, D, D and ABC, EEE, I guess, are both balanced. I don't like the word and there. It looks like it should be a letter, so I'm going to try putting my balanced numbers in boxes. Then d times d times d, d cubed is a times b times c, but that's also e cubed. And you can conclude d and e must be the same. Okay? So we can't have the product 4 times b times c be a cube. Or let's say be a product of 3 distinct digits. Because that would give me at least 6 different numbers, and I want exactly 3. Nor can this product possibly be 3 different cubes. So we must have 4 times b times c equals a square times e, and cannot be written as a cube. Okay? This will ensure that I get 3, but not having a cube and not having 4bc be a product of 3 distinct digits means I won't get an extra one, or I won't get 6 extras or anything like that. Okay, so now I know at least what I'm looking for. We've done a little dive into the theory. So what could b and c possibly be? How can I force it to only be expressed using a square of one digit and a product of another? Well, one way to do that would be to sort of shoot for really high numbers. Okay. Another thing we could do, we saw how 5 worked in part A, so we might look at 5 again, or we might look at primes. Okay. In fact, I think it's a great idea to look at 5, period. 5's kind of a big single digit. So we could try something like 4, 5, 5. Okay. I see this as the product here is 100. Okay. And so, all right, 100. Now, if I wanted to write this as a product of single digits, what would I have to have? Well, 5 divides 100, so 5 divides at least 1 of D, E, and F. By the same reasoning as in A, we see either D is 5, or E is 5, or F is 5. Okay? Let's just say D is 5, because remember, we can rearrange them and get more numbers. So let's say D is 5. Then E times F would have to be 20. Well, 5 divides 20, so you don't have to repeat the argument. You can say either E, so that means E is 5, or F is 5, but let's just say without loss of generality, E is 5. And then that forces F to be 4. There's only one way to write 100 as a product of single digits, and that's with 2 5s and a 4. So if we let B and C both be 5, then this has only 3 possibilities. Okay? 100 is not a cube, and we can see we're sort of exploiting primes here more than anything. So I suppose this could probably work with 7 and a 7. But I don't think it could work with 3 and 3. So let's just briefly talk about that. 4, 3, and 3. There are other ways. This gives me a product of 36. There are other ways to write 36. I could have 1, 6, and 6. I could have 9, 4, and 1. There's lots of things that could go on with that one. So you got to be careful. But with 5 and 7, there's only one single digit that would work. And that same argument from back here. B needs to be a digit. B can't be 0. 5 divides B. That only works with B is equal to 5. If we had said B is a digit, B can't be 0. 3 divides B. You could have had 3. You could have had 6. You could have had 9. You would have had a lot more possibilities. So it would work with 5. It would work with 7. Could we work with other big numbers like 488 or 499? I mean, we don't need to worry about this because obviously we got an answer, and that's all they asked for was just find a digit. We justified it, sure. Well, I suppose I could trade any 4 and a 9 for 2 6s, so that one would be out. 488. You're just juggling around powers of 3, powers of 2. So I feel like this one should work. Somebody who wants to, who tried this one out, feel free to confirm down below. But I'm gonna move on to part C. I think 488 should work. And of course we could have 4 and something else. That might be, well, no, because if you did 4 and something else, like say 7, just to bring back the primes, you could also do 2 8 and 7. So no, I think there might only be a few. It might be 477, 455, and maybe 488. But somebody else confirm it down below. I want to move on to part C here. Okay, so what does C say? For each of k being equal to 4, 5, 6, anything through 10, either determine with justification, again, we just want one, an integer ABC, which they're exactly k balanced integers that start ABC, or explain why you could never find such an ABC that gives you exactly k balanced positive integers. So we just talked about sort of how to get exactly 3. And in fact, in the process, we also talked about back here how to get 3 for your ABC, how to get 1. If ABC has a product gives you a cube, you've got this one possibility waiting for you. Or if ABC can be written as a product of 3 different single digits, then you can get 6 of them. So that's kind of interesting. We already talked about that, or we could have started talking about that now for part C. We can say, as we saw in part B, if we fix an ABC at the start, in B part we fixed the 4BC, but general ABC, and we get, I don't know, groups or bunches of 6, 3, or 1 balanced numbers. Depending on how the product A times B times C can be factored. Okay. But we also, just because I was worried that there might be a way to do 4BC and then have 3 different cubes, we also did briefly see that you can only get the one once. So you can't somehow get 3 cubes lying around, because they'd all have to be the same digit repeated over and over again. So I guess what we can say, so we also saw there is at most one group of 1. So since they come in groups of 3s and 6s and possibly 1, 1, the possible k must look like 6 times something plus 3 times something plus z, and z is either a 0 or a 1. But I guess we can really say it looks like 3 times something or 3 times something plus 1. Because these are multiples of 3 already. And then you either get no groups of 1 because you're not looking at a ABC multiplying together to be a cube, or maybe you do get a cube. Okay? And that should rule out some of these. So 4, 5, 6, 7, 8, 9, 10 were the ones we're looking at. 4 to 10. So you automatically can't have 5 or 8. And I wonder if that's just it. But we can't just say, all right, the others must work out, we actually would have to show it. Can we actually show 4? Can we show 6 ways? 7 ways? Can I find ABCs for each of these? And we just need to find at least one. We've explained why the 5 and the 8 won't work, but now maybe the rest of the question is just going to be find me that ABC that does exactly 10 and show that it does exactly 10. Otherwise, it doesn't really count, does it? Okay. So, more than that, just because 5 and 8 are out, just because they're congruent to 2 when you divide by 3. 4, 7, and 10 all leave a remainder of 1. They need a cube. So they need, let's say, A times B times C to be equal to a cube. Whereas 6 and 9 don't. And they can't have a cube. So we, we might treat these cases separately and try and see what we can do. And you'll notice 9, just planning ahead, 9 would have to be 6 plus 3, I think. Or maybe 3 plus 3 plus 3. 10 would have to be 1 plus 3 plus 6, or 1 plus 3 plus 3 plus 3. 7, 1 plus a 6, or 1 plus a 3 and a 3. 4 would definitely have to be a single cube and then that d squared times e stuff. Okay? But because these ones need a cube, what we could do is we could say, well, what if A, B, and C were that cube? You just need A, B, and C to be some sort of product. So let's look at A equal B equals C to show whether or not, and I think it is whether, but whether or not K can be 4 or 7 or 10. In some of these it might work. For some reason, maybe 10 doesn't work. We don't know. But let's see. So if ABC is 1, 1, 1, the product there, I'm going to try and be organized when I do this. So I'll probably have to go on multiple sheets, but let's say A times B times C, we'll say it's 1, 1, 1. And their product, actually, I got this backwards the way I want it. A equals B equals C, we'll say it's 1s. And then what's the product? The product is 1. And we can see only one way to write this. So there's only one balanced number that starts with all ones. Okay? Not particularly interesting. 2, 2, 2. The product there would be 8. How many ways could we write 8? Well, we could have another 2. Well, you could have 2, 2, 2. Or we could have, if you have just a 2, then you're left over with 4, you could have 4 and 1. That leads to 6 ways. If you start with a 4, actually, if we start with a 1, you could have 2 and 4. We've already done that. We could have 8 and 1. Well, let's try and be organized here. So let's work with D being less than E less than F. So you'd have 1 less than 1. That's fine. There's only one thing in that group. Here you could have DB1, EB1, and then 8BF. And since I've got 2 the same, 1 different, that will be a group of 3. I could have DB1, EB2, and then F would be 4. And that would give me a group of 6. Or I could have 1 and needs to be another multiple of 8. This would have to be 4. That would have to be 2. That's not going to work. I could have 2, and then E needs to be at least 2, but at most 4. So it could be 2, and then 2, and that gives me a group of 1. That's a total of 10, because you can't do 2 and 4 and then something even bigger, because your product's already 8 at that point. All right, so that sort of forces it to be 10. So K can be 10. Great. That's what we suspected would be true. With 3s, your product's going to be 27. You can get one 1, yeah, you can't do 27, so that's too big. How about 1, 3, and 9? That would be 6 different ways there. You could have 1, can't have 3 again because you have 9. If I put a 9 there, I'd have to go 3. So let's not start with 1. Let's do all 3s, and that would be one way, and so that would be a total of 7. So k could be 7, k could be 10. How about, well, we know 7 and 10 would work, and we know you need to look like a cube if you're going to be 4, 7, or 10. You're not going to get a 6 or a 9 this way. So really, we're just looking for 4. So if we race through this and here the product is 64, and we find at least one way of doing something like 6, for example, 1, 8, 8, that would be 3 ways to arrange that. 2, 4, and 8, that'd be 6 ways, so not going to be 4. 5, 5, 5, 6, 6, 6. The 5s are interesting. 1, 5, you have to be 25. So there's really only one way to do the 5s. Similarly, there should only be one way to do the 7s. If you're curious, it's 10 ways to do the 4s, one way to do the 5s, one way to do the 7s. The 6s are going to be interesting. 216. Let's see, you could have 1, 6, and 36. I don't think so. In fact, you can't use a 1. But we could have 2 and 3. You'd need to make a 36. 4, that would be 8. So I'd need a 27 there. That's not going to work. 6, then I would need 3 times 6 for what's left. 18's too big. How about a 9? That's 18 of it already, but I would need a 12 left. So I don't think we can do 2. Probably can't do 3 either, but let's try it out. A 3, an 8, and a 9 would work. So that would be 6 different ways. And you could get a 4, a 6, and a 9. That would be 6 different ways. And of course, you could do the 6, 6, and 6. But that's already 13, so we don't care about that. How about if we had all 8s or all 9s? Could we get one sort of cube and only one other possible way to do it? Because I need a group of 3 and I need a group of 1 to add up to 4. That's what we want. And if we can't do it, then maybe 4 is just too small to work. So how can we make 8? And it would need to be a group of 3. So as soon as I get a group of 6, like we've been getting a lot, the whole thing falls apart. Let's see, we could have, I think 8s and 9s are too big, actually. Because even if I try the biggest factor of 8 that I can work with, 4 here, even if the next 2 are 8s, this isn't going to work. So only 1 there, and similarly, there's only going to be 1 here with the 9s. The next biggest thing would be 3, and even if I had 2 9s, the biggest possible digits I could have, it's not going to work. So you'd write that up a little nicer, but essentially what's going on here is these are too big. Okay? So k could be 7 and 10, but not 4. And we also already know not 5 or 8. But now we've got a different thing to look at. Can I do 6? Can I do 9? That's our new task. And I think we can do 6. We could probably just reason it out, but I think if you did something like 1, 5, 7, you'll definitely get 6 there. Okay? So I'm going to do it a different way rather than making big lists. I claim this will work, and I'm using sort of the primes that we've seen so far. So if d times e times f is 35, then 5 divides d, e, or f. And as we've seen in part A and part B, we can just let d be 5. So this leaves e times f to be 7. 7's a prime, so 7 divides e or f. And if we let e be 7, again, the prime thing's going to work. Then f must be 1. So with 3 different digits, we get 6 numbers as claimed. But we've shown that it would have to be a 5, a 7, and a 1. Okay, so you can't say, all right, yeah, you get 6 numbers, but do you get others? No. So 6 works. Now it's just down to 9. So what would 9 look like? It could be a bunch of 3s. I think it might be a little easier to do a 3 and a 6. Let's see if we can think of one. Because we don't really have an easy plan of attack like that cube stuff. And we knew 4, 7, and 10, if they were going to work, they had to look like a cube. A times B times C had to be a cube, so why not just let A, B, and C be equal to make a cube? So the A, B, and C individually don't matter, it's just their product. So what would that be? I'd need to have a digit squared times E, but I'd also need to be able to get different digits. Now, if we tried having like 5 squared, then that would, just as it did when we did 4, 5, 5, that would force 2 of these to be 5s. So we can't do 5 squareds or 7 squareds. But we might be able to let E be 5. So what if I said A, B, C equals like 5 and then something like 2 and 2? Right? Because then I'll get my square. So then D times E times F has to be 20. Okay. One of them is 5, just as we've seen in part A and part B, and you would say that off to the side. So you could say let D equal 5. Then E times F has to be equal to what's left. E times F has to be 4, but E and F could be 2, or, and this is clear sort of from the 4 that this is the only possibility, or E is 4, F is 1. Okay? So 5, a 2, and a 2, there's 3 ways to write, or 3 numbers. But if you have a 5, a 4, and a 1, because they're 3 different numbers, we get 6 new numbers. And we could even write them out. Yeah, so I'll get a total of 9 numbers starting 5, 2, 2. You don't have to write them out to prove it. I've got a little bit of time, so I figured I'd will. 252, 225. So those are the 3. But then there was that other way, because there's only 2 ways to split 4 into a product of 2 numbers. So we could have 145, 154, 415, 451, and oh, I've got one too many of these. Or 514 or 541. And that's going to be 9, and I've explained why it will only be 9. I chose, you could have done 722 as well. Or 733, I think would also work. It's just based off, you're only going to get 2 different ways to do this, because 4 is a prime squared. A prime single digit squared that also happens to be a single digit. So, yeah, so 733 would have to work, 533, 722. I think these would work. There might be more. If you have any more, by all means, let me know down below. There are lots of different ways to get 9, I would guess. But these ones just follow this particular pattern based on the prime stuff that we saw in A, used in B, and are using again in C. And I like it when that happens. There we go. So to sum up, K can't be 4 just sort of based on exhaustion. It can't be 5 or 8 because you can't have more than one way to write a product as a cube. That sort of ruined that. K can be 7 and 10. We saw those just by sort of filling out that chart. And it can be 6 and 9. We sort of reasoned our way to these ones. And that should be it. All right. So that's it for our 2017 intermediate paper. Thank you guys so much for watching. If you had other approaches, other ways of looking at these numbers, maybe not based so much on the prime work that I was doing, and if you had different answers in B, by all means, leave a comment down below. But thank you guys for watching nonetheless, and I'll see you for more math in the future. Until then, take care.